Hello everyone, in this video I'd like to discuss how can we implement the lagging function in the PLC. Firstly, let me introduce the background of this topic. Okay, one typical system, we have the controller. Typically, control strategy, we could use the PID to control water level, heater system, or pressure of the water, right? Then this controller control object will go to control our control object. Typically, we call this process object. And this process object, including the actuator plus this process. And this process including the heater system, water level, motor position, and so on. And then we are using the sensor or encoder to measure this process object, typically sensor or encoder, right? Then measure this feedback. Then we feedback this value go to the controller. This is the one real control system, this diagram. Then in the real case, if we are waiting for this real process object to be assembled, to be installed, waiting for that's ready to be tested, it will need a very long time. We have to pre-program something to get our program ready for this real system. Then this will come up a topic that named virtual commissioning. The key idea is we need to figure out some way to simulate this process object. Then using the algorithm, using the math to simulate this process object, and using this simulated object to test our controller parameters, typically tuning the PID parameter. Right? So how to simulate one real process object. This is the main background of this series video topic. For example, we talk about how to determine the first order transfer function, how to determine the second order transfer function, how can we deal with the initial status is not 0, and how can we do the integrating function, for example, the servo motor positioning or the water level, right? They all showing as an integrating function. So in this entire playlist, we were talking about how can we use the math to simulate one real process object. Then one important topic we are talking about in this video is the lagging function. Basically, 95% of the real process, they all show the delay behavior. For example, in the industrial system, if we are using a pump, using the VFD to pump the water, right? This is the water pipe here. And then if we set up the pressure sensor here and try to control the pressure in this water pipe here, then we are using the VFD, using the voltage to control the VFD to adjust the speed of this pump. Then we are using the pressure sensor feedback as the feedback loop to control this VFD. If this sensor installed very close with this pump, then you can think about if we apply a voltage to this VFD, this is the voltage, then we will see the pressure could be increased very fast, right? This is the pressure. However, most of the cases we will find the pressure sensor will be installed at the user, the water user area, right? Probably could be 100 meters away or even kilometers away. But we are trying to control this pressure by using this pump. The process in the middle could be a very long away from this control source actuator. So this pressure real system will show a strong delay behavior. Typically, if now we apply a voltage to the VFD, then we will not see the water pressure increased very soon. But in the real system, it will show a very long delay. Then we will see the pressure going higher, right? So from the signal we applied, from the control signal we applied from here to the moment the object system give us some reaction, then this time we usually call this the delay time. So in this video, we will talk about how can we program this delay function. In one hand, we need to program the real function of here. For example, this is the first order or second order system. Then other than this, we also need to program something to show this delay behavior. So delay plus this real first order or second order behavior plus them together, this will show a much more real behavior of one real process object. And from the model wise, so if this purely transfer function is a GV, so this entire transfer function at the Z domain, that's equal to G Z equal to JVZ times Z minus D. This minus D is at the power area. And this equal to the YK over IXK. IX means the input, Y means output. Sometimes use the UK means the input. Okay, and how we can know the D here? The D means the times of the sample time. For example, in the real case, if the delay time is 10 seconds, and to run this equation, the difference equation, the sample time is 0.5 second, 500 milliseconds. Then the D is equal to the delay over the T sample time. This equal to the 10 over 0.5 equal to 20. So here it will be the Z minus 20. So when you see the minus 20 or minus something here, that means this transfer function need to involve the delay, need to involve the lagging feature. And again, so this is purely the transfer function, first order or second order transfer function. But once we see these things here, that means this entire transfer function has the delay, has a lagging feature behind. And here means how many times of the sample time. And just to keep in mind, this D only doesn't mean the second. So it totally depends on the sample time you are using. And then using the real delay time and the sample time, you can calculate the D. Again, I will write here, this is the GV, Z. And this is the multiply the Z minus D. So the minus D means the delay, lagging feature. Then how can we use the program to simulate this delay function? From the programming wise, actually this is not difficult. So let's turn to the next page. So still, this is the pump and this is the pressure. This actuator here to this controlled object, they have some certain distance here. So in this real system, when you apply a real voltage, we will see there's a very long delay, right? It's going higher after that. So if we apply the 1 voltage, and then we will see the pressure feedback. We can think about this area to here. This is the delay. If we can use a data array here, this array index 0, and this is the index 9. If we assume this delay time is 10 seconds delay, and every slot here, this is the 1 second. So that means if the first data, when we apply a signal, when we apply a control signal here, this is the index 0. Then after this, next time, this value will be shifted here, will shift here. Then after the next second, it will be shifted here. Till 10 seconds after, this value will be here, our control signal. Then this input will be used as the actual input for the first order, second order, or any other transfer function. The real input here after the delayed. Our real command actually come from here, but this is our transfer function input here. So we need to program something to do this array. Basically, we can buffer our control command. Then the next question, how large of this array we will need? Or specifically, how many items in this array we have to use? This depends on the sample time and our delay time. For example, in this case, if the TS is 1 second, and if the delay is 10 seconds, that means this entire buffer, we need to do the 10 slots here. to store 10 data on the way, right? That means basically idea, this length is equal to 10 seconds over 1. That means the delay over the sample time, okay? Similar idea, if the sample time shrink to 200 milliseconds, 0.2 second, then the items, the array length will have to use the 50. So when we apply the one control command, then after 10 seconds, then the final output will use as our real transfer function input. This is the transfer function input. Okay, so we will program something to implement this idea. And in the programming wise, we can declare a very long array. Then we can use the items within this array. We need to make sure the array length depends on this delay and the sample time will not overflow from this array. So we need to declare a proper length of this array, and also we need to take care about this delay and our sample time. All right, let's turn to the programming platform. All right, in this case, I will use the Siemens TI Portal platform, and I will use 1500 PLC, and I will use PLC Sim to show how can we program. Actually, this program will be very easy. So not only for the Siemens, any other platform, Codesys, and Brandly, Omron, or Backoff, you can use the same idea to program them. Okay, so firstly, I will create one function. So basically, we will create one area we can program. Doesn't matter function, function block, or program. Let's call this a login, okay? And the ICL. And the reason why I'm going to use the LCL or structure test, because to program the FIFO, first come, first out. So we do need one for loop there to shift all the items in one array. So I will manually program this. To show this common idea, I like to use the pure logic like a for loop to show this function. Okay, so FC login. We will program something here, and before we program, we definitely need to declare some variables. I will create one data DB, and this DB we can call that a login. Okay, login. Okay, in this DB we will declare some variables we will use. So firstly, very important, this is the array. So we can name this array is going to store all the data in this buffer, run as a buffer. So data type we will declare as array. And this array, the length, we will temporarily declare a length, this is 100 items. So that's starting from the 0, the length is 100, so the last item is 99. Definitely this 99 here can be replaced as one constant value. But to show this common concept, because different platform maybe use the different way, to show this common method, I will use the solid number here, 99 here. And the items we will declare as array, the float. Okay, and we do need a retain. So in case we shut down the controller, and we better retain all the data in this buffer. Okay, in your row case, maybe you will have to increase the length of this array. Okay, then we will declare the input. The input original, this is the data before the delay. Okay, this is the rail. Okay. Then this is the input after the delay. Okay, this value actually, this is the output of our entire function. So this eventually will be used for other transfer function, but this is the after the delay. Okay, this is the Y, after delay. Okay, and then to program the for loop, we will definitely need an index value. So the index, this is the integer. Okay, and we also need some setting. The setting, that's the time, this is the delay. Okay, for example, if the delay is 10 seconds, so this value will be the 10, and the unit. So here we can write here, the unit is a second. Okay, we will declare this as a real. Okay, and then other than the delay, we also need to define the sample time. The sample time is a TS here. Okay. Okay, then basically we declare all the variables we need. Now we can shift to the function Then we can start programming here. So firstly, we will program very important concept. That's the shifting the array. Again, if we go back to this concept, so this is the array buffer we have now. Anytime when a new data come in here, the new data always come as the 0 index. Basically, you can understand this. If this go to the vertical, this 0 is at the top of this array, right? Or at the very left side of this array. Then before we insert here, every item will shift it one item from left to right or from the top to down. So 10 will be override by 9. After 9 transfer, then 9 will be override by 8, right? After 8 transfer to 9, then 8 will be override by 7, okay? Then at the end, so 2 will be override by 1, and 1 will be override by 0. Then at the end, 0 will be override by a new input data. So this is the idea. So we will program a for loop. That for loop can execute this shifting one by one. Okay, let's go to this program. Then there's one very important idea. We need to firstly calculate what the length we need from this array. So that calculation actually is equal to the delay time setting and derive the sample time. Okay, derive this sample time here. Okay, then we need to declare one variable can store this. But when we declare this variable will be used as the for loop. While we are doing the for loop, this number need to be an integer. From here, we will declare this is the length of the actual we need. So here, while we are calculating this value will be a real, will be a float. Then we need to convert this float into the integer. So from here, we will convert the real. We will convert a real to an integer. Okay, so we will bracket that. So key idea is the result of this calculation is a float. So we need to convert to the integer. So the result is this length actual here. Okay, then after we got this real length, then we will program that loop. So we will firstly program this very core loop. So we will use a for loop. So for loop from this index, we will use this index starting from the 0 to this counter calculation result. Okay, then so this is and the for. This is the for loop, and within this for loop, we need to do a shifting, just one line code. To do this shifting, so we will use this array. Okay, this array. So we will drag this array here. Then we will do the shifting from the bottom to the top. So the bottom, we will use this array length minus this index. And plus 1. Always the one item further. And then this will be override by the one item above. We will copy this area, but this time the right side of this equal doesn't have this at 1 here. We'll delete this. The first time when this index equal to 0, we will see this is the bottom of this buffer. And the bottom of this buffer will be transferred to the bottom of this buffer at one item. Then at the end, when this index equal to this one, so the right side here is a 0, and this is the 1. This is the same idea as here. So 0 to 1, and then do 1 to 2. So you need to make sure from the bottom to the top, right? You need to make sure doing from the right to the left. Okay. All right. So this is the array shifting. Then the very top of this array, this will come from the new data. So after the shifting, after this for loop, then the new data will be copied to this 0 index. Then the new data is this original, right? This is the new data. Okay, and the very bottom data, so consider if the array is 10, because we're starting from the 0, so the last item from this array that actually equal to this counter, this item minus 1. This is the last data, and this data is a ready data showing as a delay behavior. At the right side of this equal, then this is our result. Okay, we can drag this to here. Okay, as we can see here, so 0 will be used to store the new data, and this last item of this buffer then will transfer this delayed result. So this delayed result will be used as the real input for our transfer function. Okay, and so after this delay, the last item here will be used as a real input of this transfer function to show this entire behavior with a delay, and then we have the real, this first order or second order behavior here. Then we will see, so while we are transfer here, to prevent the array has overflow, for example, if this length is equal to 0, this index will equal to -1. This is not acceptable. And also, so this area here must be less than the 99. Otherwise, this calculation, this index here will overflow the maximum of this array length, right? There are something we need to be a little bit carefully. So we will add one if here. We will add if else here. This length actual -1 greater or equal to 0. Then we will do our logic here, right? 0. Else, then this delay can directly equal to the input, right? So the delay is equal to the input original, this one, right? This is the if else, okay? And don't forget the and if, this item need to greater or equal to 0. Then we also need to guarantee this portion less than the maximum length of this array, okay? And our array, the index from 0 to 99. So this highlight portion need to be less or equal to 99. So we need to put an if inside this for. If this portion less or equal to 99. So here 99, I'm using the direct number. But in the real case, you can use one constant value to define your array maximum number. And also here you can use that constant variable. So once you change the constant variable, you can change everywhere, okay? And this if, and we can do and if, to make sure whatever this for loop runs, so this index here always less or equal to 99, the maximum index number of this array, okay? This is the two protection logic here. Before we download, we definitely need to call this function, this lagging function. And because we have this sample time here to accurately calculate this delay time, the cyclic organization block. So in this case, if our delay is 10 seconds and this cycle time is 0.5 seconds, then this buffer, we will need the 20 items, right? So I will use the half seconds. So here I will set 500 milliseconds. So take care of this unit here, 500 milliseconds, okay, half second, okay. This interrupt, this cyclic interrupt, okay, and in this cyclic interrupt, we will call this function. So I will call this lagging, okay, and before this call, I will definitely need to set these two parameters. How long we need to do this delay, and what the sample time we will run this function lagging. So I will use the move, okay, and we will set this delay time here 10 seconds. So 10 seconds we will set 10.0. Then the second logic here, we will also set the sample time, and the sample time must match with the cyclic interrupt second. So in this case, I set 0.5 second. Take care, all those values, their unit is the second. Okay, and this is the lagging. Then we will download the PLC, and I will use the simulation PLC. Let's start up the simulation and let's download this logic. Okay, now this is simulation PLC start up. Okay, now let's monitor this FC now. And as we can see here, our delay setting, this is a 10 second, and this is sample time here, this is 0.5, half seconds. So that's why we need the items from this buffer is 20. Okay, then let's go to the trace. And I will download this configuration. We will monitor the input and this input delay, and we will see the difference between these two. In the meantime, I will open a watch list, and we can monitor this input and output. Okay. Okay, this is our real input, and this is the delayed result. We will see their difference. Now we will start off this recording, this trace, and now we will give a 10 value here, and we can transfer this value, transfer. Then we will see this buffer, how this buffer run. We will see along the time, then this buffer will be filled. After 10 seconds, we will see this blue line will be turned on. So this is the delay. Okay? So we will see achieve this function here, and we can stop this trace. I transfer this input from this 8 seconds. After the 10 seconds here, got this output here. Then this blue line, this variable, can be used as the real input as our transfer function. So we can use this logic to simulate this delay behavior. Back to this picture here. So we apply an input after this 10 seconds delay. Then this logic output can be used as the real input of the transfer function to show this delay behavior. Then the result of this transfer function can be used as the real feedback for your controller to facilitate the commissioning for your controller, to tune your controller parameter. Alright, this is the idea to implement this delay feature. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.